Okay, so welcome to the third part of the series Exploit Development Under Linux, and my name is Himanshu. Let's continue. So, in the previous part, what we looked at, let us see what we have done till now. So, in the previous part, we looked at how to exploit stack-based buffer overflows, in which this was a very vanilla kind of vulnerability. It was just a huge space, and then we overwrote the return address. Now let's look at some other scenarios. Now let's look at the NX memory protection. Now NX or no execute is a protection mechanism which forbids execution from the pages which do not have permission to execute. Now it was implemented first by AMD, and then Intel introduced the execute disable or the XD bit in their processors for the same effect. Now what this does is now we have two types of pages or data inside memory. One which is executable, which is your instructions, and another which is just plain data such as local variables and things like that. So what this does is it kind of separates those things, and it tells whether you can execute something in memory or not. For example, if this is instruction, it can be executed. If this is data, it won't be executed. Now what Linux does is, or what open systems does is, they have memory protection feature named write or execute, which is their way of implementation, saying that this page is whether it can be returned to or it can be executable. So now what you have is whether a page, whether it contains some data or it contains instructions. Let's just see how it is in practice, then we will move to looking at how to how to exploit those things. So let's look at get. This is the program, and yes. So this is the PID of a cat program. So let's just copy and let's see its memory map proc PID and then maps. So what you can see is this is the memory map of the cat process. Now these are the memory ranges. This is the starting and this is the ending of that particular segment or section, whatever you would want to call it. Now these are the permissions on these memory mappings. So have a look at the stack. This is readable, this is writable, but this is not executable. And this thing, this is executable, but it is not writable. This is the first thing which where our main is mapped, or where our code is mapped generally. So you see now this is another executable area is this one, which is the GNU libc shared library or the shared object. And another thing we have is this is PDSO, and then this is LD shared object. So this confirms that write or execute thing which we have, which means is now what we have to do is, if we want to make it executable, we, as we did in the last part, we pass the flag -c exec stack to make the stack executable. Let's just have a look at that program. Yes, ls, and that was basic, right? So the PID is 3279. Now you see, since we compiled our basic program last time with the executable stack function, here we see that the stack section is readable, writable, executable. But the binary which is not compiled with the exec stack switch does not have the executable bit set. Now, what to do in this part? We will be looking at what to do when we have a non-executable stack. That means you can put your shellcode on the stack, but you cannot execute it. Now, this protection is quite interesting because this totally disables the execution part. So when you are able to put your shellcode but cannot execute it, that becomes a problem. But what this protection does not do is it forgets that we can still corrupt the stack and we can then control the return address. So it is not important for us to control the return address just to point back in our stack. We can point put it in the text section. Now, pointing in the text section or pointing in the executable code has multiple variations of a text. One is return to libc, which we are going to discuss today. Then one is return to text, in which we just kind of return to very simplistic or very minimalistic forms of execution. And another is return oriented programming. Now, we will be talking about return oriented programming in the upcoming parts of this series. So just wait for those parts. Now, another thing which return to libc offers is that, for example, the vulnerable code for today is this. Yeah. Now, we will see how to deal with the non-executable stack, but today we have another twist, and that is we have the vulnerable function reflect back. It just takes an input into the buffer, which is of 8 bytes, and just prints it back. So another problem we have is what to do when we don't have enough space for a shellcode on the stack. Now, let's first worry about the shellcode part, and we will see about the execution part later. So say we have only 8 bytes here. Now, even if we are able to override this 8 bytes and then the save dpp, then the return address, we cannot really kind of put anything usable in this program. Now, what return to libc does is, okay, before moving on to the exploitation strategy, let's just think of if we can place our shellcode somewhere. So the strategy is to place our shellcode somewhere in memory, but which is not on the stack again, and try to get it executed. Now, in this case, return to libc attack, what we generally do is we perform a return to system attack, and in the return to system is we override the return pointer of this function to the port to the function system. Let's just have a look at what system does is man to system. Sorry. Now, this is this function. It executes a shell command. So what we are going to do is we are going to place our system shell command in an environment variable, and then we will retrieve the address of that environment variable inside the process memory, and then we will just pass the address of this as argument to the system as it specifies here. Then it executes that and it returns after the command has been completed. So now the question comes is what to do when it returns, or what will happen when the system returns. Then it will get, again, since it has nowhere to return because we have corrupted the return address, so it will probably crash. Now, to overcome that thing, what we can do is we will just override the next or the return address where the system will return with the address of exit function or the exit system call. Then exit, this is, so we will call exit with the status 0 so as to just kind of gracefully exit. So now it will look like this. We have chunk, saved EBP, then we have EIP, saved EIP, of course. Now when we are overwriting it, we will just saved EBP just will be part of chunk again, and we will override it with the address of system. Now once the system will return, it will now the next entry on the stack will be used as the return for the system function. So we will just make it return to exit, and then we will place the call or the address of our command on the stack, and then since we are going to exit, let's just put null, because since we have a gets function, it won't give us any problems, right? Let's just see what happens. Now this is the basic idea that we will be working with. Let's just compile the, let's have a look first. Space.c, this is it. Okay, oh sorry, it has a string copy. Again, let's just see what happens. GCC. Okay, so we have compiled it with the no stack protector so that there is no cookie and things like that. Then we have set the m preferred stack boundary to 2, just to stack an element as in the integral multiples of 4. And if you notice, we haven't used the -c exec stack in this compilation, which we did in our last program. So let's test what it can take. No space, it takes an argument. So yeah, since there are only 7 bytes, let's just do this, and we have this thing. So there is no room. Let's do this. Let's see how much space we have. So we have 8 bytes here and 4 bytes of the EBP, right? So after 12 bytes, we are going to overwrite the EIP. Let's just verify that in GDB so that we have idea what we are working with. Break on, reflect back, run with eight A's, 4 B's, and 4 C's. Now disassemble, and let's just put a breakpoint at this address at the return pointer, at the return instruction of the reflect back function. So break reflect back plus, let's see what was that, 66. So let's continue, and if you see at the top of the stack, we have our C's, which were the after 12 bytes, and if I press SI, we see this, and you can see that EIP is pointed to this. Now we can see that we are able to overwrite EIP with just after 12 bytes, and now the question comes how to move to exploitation part. So let's have a look at strategy. This is, so these are 8 bytes, right? This is 8 bytes for the buffer, then we have 4 bytes for this thing, and then we need the address of the system. So let's first take the address of the system. To do that, the program must be in the running state, so let's just run this. P system, this is the address of the system, so let's just copy and save this thing, right? And let's just to gracefully exit, let's just get the address of the exit. This is the Okay, so we have the address of system, we have address of exit. Now what remains is to place a command in the environment variable. So when the program starts execution, or when the program loads, the environment variable gets loaded in the memory, and therefore our command, which is what we have put in the environment, will also be inside the memory space of the program, and therefore we can reference it, or we can obtain its address and pass it so that system can execute. Let's first place. So now one thing, I am using the netcat.traditional package, which does not by default come with Ubuntu. The by default package that comes with Ubuntu is netcat openbsd package. Now the problem with the netcat openbsd package is you cannot execute commands. I mean, you cannot do this then bash, because it is not supported by the openbsd package. If you want this is in the netcat traditional package, which you can just nc.traditional, right? Right. Okay, so let's just search nc.traditional if we have this thing. Oh, okay. So to install that thing, you need to do netcat traditional. Install netcat traditional, and of course I cannot install that because I'm not yet. I mean, I have this thing, and see, I already have the newest version. So to use the netcat traditional package, you do nc.traditional, and let's just try to listen on the port 4444 and execute, then dash. See, it's working. So let's just try to connect here and see if this works, and if this works, we can then use this as the command to get executed from a vulnerable binary. Now nc 127, and we get it. So it is working. We get a shell. It says it got a connection from the local machine. Great. So it works fine. Now to put it in an environment variable, just we are using export and an environment variable name equal to sign and the string which it needs. So let's name it port, and we are just loading it. So to verify, it has been loaded inside the it has been loaded as an environment variable in the shell for this session. Let's try to print its value, echo port, and we get here. So we have this. Now the question comes, how to retrieve the value of environment variables. To do that, what we have to do is we have to write a C program or and the script, whatever you would like to write. All you need to do is get environment variable, man get env. Now what this function does is it gets an environment variable, or it returns the location of environment variable. The get environment function searches the environment list to find the environment variable name. So in the get environment, we will be passing the name port, because that's the name with what we have exported our environment variable, and it returns pointer to the corresponding value string. So it returns pointer to the string and not to the port. And like, see, you will see what I'm talking about. So get environment address.c. This is a very simple program. It just does the get environment and prints its address. So get environment address. Let's just compile this. Get environment. Here we have it, get environment, and since we exported that with port, so we see port is at address this address. Now we got the address of our environment variable, but since we want it inside the program execution and things change a little bit because of differences in environments. So let's see what happens. Let's just copy this value and print a string at this location from our program, right? Main, let's just run this thing and examine a string from this location. See, now this is the location after which there are no string, it's empty. So we are probably, our environment variable is probably behind this. So let's just do probably 68, right? Okay, so we can recognize this part, right? This is what we exported, and since we want this is what we want, and if we just subtract 1, you see port. So we do not want these 5 bytes because if we pass this, then system will try to execute this as a whole, and since this is not a system command, or this is not something that the system can execute, we just need this part because system will execute nc.traditional as a command line. So 60, that's 68, and 4, that's like 6b something, right? 60. Okay, so this is the address that we need to pass or add this. Okay, so let's just do this thing here. So the address of our command is this, and null is, well, zeros. So let's just quit and let's write Python script return to libc.py. Now this is it, and the address was 6c, right? So let's just write it 6c because that's the address of our traditional, and this is the structure of our exploit. So 12 bytes, 8 for the buffer, 4 for the saved EPP, then the address of system, then exit, and this address of the environment variable, and then we have null. And finally we just print it because we want this as an argument. So let's just no space and execute our binary. So okay, now something happens, and what happens is not what we wanted. We see that shell says 00 not found, and it says something which was definitely not this. So what happens is this address is, since it was loaded in the debugger, and when we load programs in debugger, some extra things are added in the environment, and therefore things change, or actually the offsets change. So let's just find out where this is, or where this string is, and then what we will do is we will compute the offset of this string from this string, and since this is behind since this is behind this string, we will just add the difference so that it becomes pretty good, right? So let's just back it main, and let's just run. Okay, so this is what we wanted, right? Now at this location we have in the debugger, this is the location that we had put. So let's just try to go some bytes back, and for a 3D, let's just see this. Now if you see what we had back there is, yes, we had 2 zeros, 36 something dot opus 00, right? So we had this. So let's just try to make it 3a. Okay, so this is probably what we had, right? 0 0, then 36, then star opus, right? And okay, 0 0 not found, 36 not found. Now this not found is because of this thing. We have semicolons, and the semicolons are used as terminators in the command line. So if you try to execute 0 0, it will say let's just see how it works. 0 0 and 36. See, 0 0 not found and 36 not found. This colon, this semicolon actually told that these are two different commands and execute them. So since both of actually neither of them is a command, therefore we had two error messages that this is no. So this is where we have our string. Actually, this is what our program has at the memory. So let's just print the difference, which is, I just take the last 3 bytes, right? And what we had is F6C, right? F6C minus F3A. We have 50 bytes. So when this program is running outside the debugger, the offset is changing by 50 bytes behind. So what we can do is, what we have to do, we can just add 50 bytes to this and FF6C, and let's just add 50. And let's print it in hex. So we get FF9E. So our address will become BFFF9E. So let's just put that in our return to libc script, change 6C to 9E, and now actually run this no space with this, and we have this thing listening on any 4444, and let's just do a netcat to this. So this way. And we have this ls. That's it. So this is in essence what return to libc. What a return to libc attack is. In the return to libc attack, what we do is we overwrite the return pointer to with the address of libc functions. Essentially, in this case we used the system and exit. You can also use any other functions if you feel like there's a return to string copy attack, things like that. I mean, you can just use string copy, then pass the address so that it probably it copies your shell code from stack to some other location, and then if you have copied that to a writable location, actually executable and writable location, which is actually the problem here. It cannot be executable and writable at the same time. So the simplest approach is to use system followed by exit. Now let us see what happens if we just exit this. We exited and echo. See, we exited with a 0. So the program did not crash. We got our shell. We didn't need to put our shell code on the stack, and see, we also bypass the no execute protection, or basically non-executable stack protection. So this was what I intended to cover in this video. So if you have any feedbacks, please do it. And this is what I meant when I said killing 2 birds with 1 stone. Now the first bird was that we had lack of space. I mean, we did not have enough space to put our shell code. And the second bird was non-executable stack, which did not allow us to execute our code on the stack or our shell code. Well, in the road ahead part, we will be taking a look at some other techniques to exploit non-executable stacks, such as return-oriented programming. Then we can also have a look add some other protections. I mean, if there is a check that whether the stack is the return address is pointing to the stack or not, then we have corrupted it and we have pointed it to a shellcode, then aborts execution. We will also look at that, how to bypass that, and in the future we will also be probably looking at heap exploits, heap based buffer overflows, and other things. So thank you very much, and subscribe to the channel if you haven't done that yet. If you like the video, press like, and those kind of things.